All right, let's get into it. Today, we're taking a deep dive into the periodic table, focusing on two huge areas, the main group and the transition elements. So, have you ever just looked at the periodic table and wondered, what's the deal? Why are some elements, like the halogens, just bursting with reactivity, while others, like the noble gases, are kind of aloof, they keep to themselves? And what's up with all the amazing colors you get from transition metals? It's pretty wild, right? Well, believe it or not, the answers to all of these questions are actually hidden in plain sight, encoded right there in the layout of the periodic table. So think of this explainer as our guided chore. We're going to go and decode those secrets together. So here's our game plan. We'll kick things off with the oxygen family, jump over to these super reactive halogens, and then the chill noble gases. After that, it's into the D block to see the transition metals, and we'll finish up with a quick review of the key trends you'll definitely want to know. Sound good? Let's get started. Okay, first stop on our tour, Group 16. You might hear them called the chalcogens, but most of us just know them as the oxygen family. This group has a ton of personality. You've got oxygen, of course, the most common element on our planet. It hangs out as O2, the air we breathe, but also as O3, which is ozone. That's what we call an allotrope, just different forms of the same element. Then there's sulfur, which makes these really cool crystal structures. And way down at the bottom of the group, you've got polonium, which is radioactive. But the one thing that really ties them all together, they love to form oxides with pretty much everything. Okay, now this is where it gets really interesting with these oxides, their acid-base character. It's a tale of two different personalities, and it all comes down to what oxygen decides to bond with. So if oxygen pairs up with a metal, you get an ionic oxide. Plop that in water, and you get a basic solution. But if oxygen bonds with a nonmetal, you get a covalent oxide, think sulfur dioxide, and that's going to make an acidic solution. This is a super important trend, one you'll want to lock in. All right, let's switch gears and look at what happens when these elements bond with hydrogen. They're hydrides. Now, if you look at the graph, you see a pretty clear trend, right? The boiling points go up as you go down the group from sulfur to tellurium. Makes sense. But wait a second. Look at water. H2O is a huge outlier. I mean, its boiling point is way, way higher than it should be. And the reason for that is a chemical superstar, hydrogen bonding. It's this incredibly strong intermolecular force that literally makes life on Earth possible. And hey, while we're here, check out the other trend. These things get more acidic as you go down the group. Why? Well, that bond between hydrogen and the element gets weaker, so it's easier to pop off that proton. So, a quick recap on Group 16. Key takeaways? Remember that allotropes are a big deal here. Metal oxides are basic, non-metal oxides are acidic, that's a big one, and hydrogen bonding makes water a total weirdo, but in the best way possible. Okay, let's keep this tour moving. Next up, we've got Group 17, the halogens. And let me tell you, if the periodic table had rock stars, these guys would be it. They are all about reactivity. So what drives the halogens? It all boils down to one simple thing. They are desperate to gain one more electron to complete their outer shell. That's it. This gives them a super high effective nuclear charge, which is just the fancy term for the pull their nucleus has on those outer electrons. It also means they have the highest electronegativity in their respective rows, so they're basically the bullies of the periodic table, snatching electrons from other atoms with some serious force. All right, pop quiz. This is one of those classic gotcha questions that shows up on exams, so listen up. We just said fluorine is the king of electronegativity, right? So that must mean that hydrogen fluoride, HF, is a crazy strong acid. It just has to be, right? Well, nope. It's actually a weak acid. And this trips up so many people. So what is going on here? How can this be? Well, there are two big reasons. First, that bond between hydrogen and fluorine is ridiculously strong. The bond association energy is through the roof, so it takes a lot of energy to actually break it and let that proton go free. And second, remember our old friend hydrogen bonding? Well, HF does it too, and it does it really well. The molecules all stick together in solution, which stabilizes them and makes them less keen on breaking apart. But as you go down the group to HCl, HBr, and HI, that bond gets a lot weaker, and those guys are all very strong acids. Okay, so halogens in a nutshell? Two things to remember. They have the highest electronegativity in their rows, bar none. And because of that, they are powerful oxidizing agents, which is just a chemist's way of saying they are really, really good at stealing electrons from other things. So we've gone from the most reactive group on the block to, well, the least reactive. We're jumping all the way to the other side of the playground to Group 18, the noble gases. These elements are the definition of chemical stability. They're like the Zen masters of the periodic table. Their secret? A perfectly filled outer shell of electrons, what we call a closed shell configuration. They're electronically happy. They don't need to gain electrons. They don't want to lose electrons. I mean, trying to rip an electron away from them takes a massive amount of energy. That's a super high ionization potential. So for the most part, they just don't react. For ages, chemists called them the inert gases, which basically means totally unreactive. But is that really the whole story? Are they truly inert? Well, the answer is not really. It turns out the heavier noble gases aren't quite so noble. Now, nobody's ever managed to make a stable compound with helium or neon. They're still holding out. But back in 1962, a chemist proved everyone wrong by making the very first compound of xenon. And since then, a whole bunch of them have been made, usually by reacting xenon with super electronegative elements like fluorine or oxygen. It's a perfect example of how in science, you should never say never. There's almost always an exception to the rule. All right, we've spent a lot of time on the far right of the periodic table. Let's head back to the middle. We're now entering the biggest, busiest, and maybe the most complex neighborhood on our tour, the D block, home of the transition metals. And this, my friends, is where the chemistry just gets awesome. So much of what makes transition metals special, the fact they can have multiple oxidation states, their use as catalysts, their ability to form these cool complex ions, and of course, those gorgeous colors, it all comes down to one single thing. They're partially filled d orbitals. You can think of those d electrons as being the source of their rich and varied personalities. So let's talk electron configurations for a minute. If you just blindly follow the rules you learned in Intro Chem, you'd expect to see the configurations on the left for chromium and copper. But reality is a little different. Take a look at the actual structure. See what's happening? In both cases, one electron from the 4s orbital has jumped up into the 3d orbital. So why would they do that? Why break the rules? Well, it's all about finding the most stable, lowest energy state possible. And it just so happens that there's a special kind of stability that comes from having a d subshell that's either exactly half full, like chromium's d5, or completely full, like copper's d10. The atom is actually more stable by promoting that s electron up. It's like a small investment for a big stability payoff. Okay, here's another really important idea for the heavier transition metals. It's called the Lanthanide contraction. So as you go from the 4d row to the 5d row, you have to cross that block of f orbitals, the lanthanides. The thing is, f orbitals are really bad at shielding. Think of it like they're a terrible screen protector for the outer electrons. They don't block the pull of the nucleus very well. So as the nuclear charge increases, the outer electrons get pulled in much more tightly than you'd expect. And the result is kind of shocking. The 5d metals end up having almost the exact same size as the 4d metals right above them. This has massive knock-on effects for their chemistry. And we have to talk about the colors. I mean, it's one of the coolest things about transition metals. So where do they come from? Well, there are two main ways this happens. First, you've got what are called DD transitions. Basically, an electron absorbs some light and uses that energy to jump up to a higher energy d orbital. This is what's behind the often pale, pretty colors you see in a lot of common metal complexes. But then there's charge transfer. This is a whole different ballgame. Here, an electron absorbs light and makes a massive leap, jumping from one of the surrounding molecules, a ligand, all the way onto the metal itself. This process absorbs light like crazy, and it's responsible for the super intense, vibrant colors you see in things like the permanganate ion, which is just this stunning deep purple. Okay, we've covered a lot of ground. Let's wrap this up with a super quick review of the key trends that you'll definitely want to have in your back pocket for any exam. First up, acidity of those hydrides. Remember, H2O and HF are the weird ones because of hydrogen bonding. But for everything else in both groups 16 and 17, the trend is crystal clear. Acidity goes up as you go down the group. And the reason is exactly the same for both. As you go down, that HX bond gets longer and weaker, making it way easier to just give up that proton. And here it is, maybe the most powerful predictive trend in all of chemistry: electronegativity. As you go from left to right across a period, that effective nuclear charge just keeps climbing. That means the nucleus gets better and better at pulling electrons in, and electronegativity goes up. Seriously, if you can understand this one trend, it unlocks the explanations for so much of the chemistry we talked about today.
So there you have it. We've seen how the arrangement of electrons really is the master key, dictating everything from how reactive an element is to the colors it makes. But we've also seen that for every so-called rule, like the noble gases being inert, there's always a cool exception waiting to be discovered. Which really makes you think, doesn't it? What other amazing anomalies and secrets are still out there, just hiding in the periodic table, waiting for us to find them?